So thanks for the introduction. Great to be back in Vilnius. I've been here only once, about 10 years ago. I've seen yesterday the city has improved a lot. It's really beautiful, always was, but it's even nicer. And thanks are, of course, to Gediminas for organizing this nice meeting. As promised, I will be talking about dipolar bosons, mainly about solitons, a little bit about rotonic states. As we all know, the early experiments with bosons and condensation, rubidium or sodium, were done with atoms, of course, equipped with a magnetic moment, but with interaction between them really dominated by the contact interaction, by the short-range van der Waals forces. However, very early in the development of the field, the quest for more magnetic or more dipolar gases has begun, and really a hero of this quest is Tilman Pfau, who perhaps is already in the audience. And after a heroic struggle of many years, Tilman was able finally to condense chromium with its magnetic moment being equal to 6 times Bohr magneton. That was not the end of the story. The quest was on. Erbium has been condensed by Francesca Ferlaino with its magnetic moment 7 times larger. And then Ben Leuf at Urbana-Champaign managed to condense dysprosium with its magnetic moment equal 10 Bohr magnetons. And that's the end of this race, because as we know, dysprosium has the largest magnetic moment among stable nuclei, stable atoms. So now, with dysprosium available in many labs, again including Tilman Pfau, with his beautiful droplet experiments, we have magnetic forces or energy of the magnetic interaction between atoms about 100 times larger than that with the original van der Waals-dominated gases. What I want to discuss here mostly are solitonic waves in such gases. And let me remind you that the approach to this typically starts with the Hartree approach and the mean field approach to the weakly interacting gas. The resulting equation without binding potential is just identical to the so-called nonlinear Schrödinger equation, and that one belongs to this restricted class of solitonic equations. So, of course, there are solitons and multi-soliton solutions that should be visible, should be available in this contact interacting gas. And of course, nothing is ever perfect. No mathematical model is really realized in nature. So there are several restrictions or several complications in this case. One is to be noted, it's not a great complication in this condensed system. Typically, the coupling constant G is positive, and that makes solitons dark solitons rather than bright solitons. That is worth noticing. Of course, always, we never have an infinite line at our disposal, so always the system is finite. We also practically never have a truly 1D systems. There is some kind of a transverse distribution of a potential. And also in the longitudinal direction, in most cases, there is a binding potential. All of this, of course, complicates the picture a little bit. However, one can generate solitons, first single solitons, and then also, say, 2 solitons in the elongated traps with the contact interacting gases. That has been done first almost simultaneously in Hanover and at NIST. And then Klaus Zengstock took this art of so-called face imprinting method with him to Hamburg. And I just want to show you a beautiful example of two oscillating solitons in such actually in the rubidium gas, rubidium condensate. One feature which will be of some importance later on is that to a very good approximation, there is an independent of interaction, independent of the amplitude of oscillation of the solitons period of motion here, which is related to the longitudinal trap period. It is omega of the soliton is the omega of a trap divided by square root 2. And that can be checked experimentally in such a nice experiment. Now, as title says, we are mostly dealing now with the dipolar systems. And in the dipolar system, one can again do something like a quasi-1D discussion of quasi-1D system. One can eliminate the transverse degrees of freedom, getting some kind of the effective interatomic potential, which is now long range, of course, just because of the dipolar forces being long range. Its tail falls off, as you expect, as 1 over z to the third power, nothing else. It is interesting that there is also a shorter range part, which is much steeper. And also it's interesting that this part of the interaction turns out in this 1D simplification, tends to a finite value at the zero distance between these two subclouds. Of course, there is some trace of the divergence of the standard 1 over r cubed potential, and that turns out to have a form of a delta type interaction, or like a short-range interaction. And just in the first papers, just to restrict our attention to the action of these long-distance, long-range interactions, we assumed, theoreticians can do it very easily and experimenters also can try, we assumed that using these Feshbach resonances, short range, the zero range part has been killed. So the only interaction that we have in our model is the one depicted in this figure. Okay, so first, single solitons. We again do a phase imprinting, do our optimization little routine that's not very difficult. And as it turns out, everything now depends on the aspect ratio between these transverse to longitudinal sizes of our system. If we have very, very narrow thing, then the shape of the soliton cannot really be distinguished from this famous Zakharov and Shabbat shape from the nonlinear Schrödinger equation. So that is not very interesting. However, as we thicken the trap a little bit, then the shoulders appear, and actually the shape is slightly different. We do not have analytic expression for that. We only have numerical solutions. Okay, that is fine. I should stress, and that is shown, that is explained here at the top of the slide, that we are dealing with in our calculations, we are dealing with something with the periodic boundary conditions. So one has to make sure that the phase which goes through a pi jump at the position of the soliton is actually continuous, so to say, behind at the other end. So there is also some kind of the linear dependence of the phase away from the position of the soliton. If we now let the system evolve in time, then we can check that actually the shape is beautifully preserved. So the solution really deserves the name of a solitary wave or solitonic wave, but one has to understand that because of this matching phase, this soliton is not standing like the one the corresponding one in the nonlinear Schrödinger equation, but is actually drifting, going around on our circle. Much more interesting is the situation with, whoops, I went in the other direction. Much more interesting is the situation when two solitons are created, not far from each other, because unlike the contact interacting solitons, these guys do interact between themselves. In the upper panel, you see the intersoliton potential that can be derived, and it has all the features of the molecular potential between two atoms, yes? So there is some kind of the ionization threshold here. And we have three starting points, A, B, and C. Now, A is the situation when we placed initially our soliton side by side, very close to each other, at the repulsive part of the potential and above the ionization threshold. The resulting motion, as you expect, is that they just travel around, travel around, travel around. Of course, they go through each other. At this stage and at this time scales, they seem not to interact while they are going through each other. If I start with the position B, which is deep inside the binding potential between these two solitons, then again, not unexpectedly, they simply oscillate like in the bound state. However, if we place it at position C, which is very close to the ionization threshold, then something interesting appears. That's on the right picture here. As you see, there is some strange motion. They collide several times and then they go away again to travel around. So they are speeding up somehow, seemingly gaining energy, which is kind of funny for a physicist, yes? Now, so we just cranked up interaction strength a little bit to really focus on this this inelastic scattering of two solitons. These guys here, as you see, attract each other, go through a collision, and then gain speed and then travel around. So something is happening at this collision point, collision region. And if you look closer, there are these little wiggles coming out of this region. Actually, this inelastic collision gives rise to the creation of phonons here. However, it resembles a little bit creation of photons when two charges scatter. However, unlike in the charges case, when they scatter, emit some photons, they have to slow down because kinetic energy should go down at the collision. Here, they are speeding up. Why? Well, because these are dark solitons, and as you probably know, many of you know, they can be regarded as a negative mass particles. So actually, to decrease the kinetic energy of such a guy, you have to make it move faster. As you probably also know, at the same time, they are getting shallower, they are graying, yes? So that's the explanation of the phenomenon. At this stage, we also decided that we want to see something really a bit more realistic. So we joined forces with our colleagues in England and did some work on truly three-dimensional but elongated trap with also trapping potential in the longitudinal direction. So our solitons are now not moving like this, but are oscillating in the binding potential. And we looked at the possible traces of the dipolar character. And here is such one thing. Again, we see that when they collide, they gain speed, yes, so the amplitude of oscillation grows as they collide. And much more interesting, I think, is that contrary to the solitons in contact interacting gas, there is now strong dependence of the frequency of oscillation on the strength of a dipolar interaction, and the strength is measured relative. This is this epsilon dd, as some people are using. We are not the first to use this parameter, which is just the ratio of the so-called effective dipolar length to the scattering length of the zero range part of the potential. So if one would like to create such things, again using this time-honored method of phase imprinting, then it will be very hard probably to see our little shoulders that I've been showing. But perhaps it would not be very difficult to see this somewhat anomalous frequency of oscillation, we think. Now, at this stage, we decided to go from many to a few and to look at the exact solutions of the finite and actually small number of atoms moving, in this case, again, moving on a circle. Then, of course, a good starting point, just a rehearsal to all this, is to look back at the Lieb-Liniger model of contact interacting gas on the circle. This is a very famous paper and has a beautiful solution. It's often called analytic solution, but it requires quite a lot of numerics to gain any understanding of the solutions. And one of the famous findings of this model is the fact that elementary excitations in this model follow two different types. One of them grows quadratically with a total momentum, and at least eventually goes quadratically with the total momentum, and that is, of course, immediately identified as the Bogoliubov branch. But there is another branch which actually Lieb and Liniger didn't know what it is. They called it second type, which bends like you see here. And many authors over the years wrote papers trying to explain or even explaining that these excitations that follow this second type of excitations in the model, they somehow correspond to dark solitons in the model. I say somehow because some people prefer to say that to build soliton out of these things, you need a couple of such solutions and to make wave packets. But some others, and including a beautiful paper by Sirvit and Saha is here, mentioned that actually if you really not look just at the wave function at the given second type excitation, but you look at the single copies of the measurement done on such states, then you will indeed see dark solitons. Following suggestion of Lincoln Carr and maybe others, we call this second branch points, energy eigenvalues, Erast states. That's the term borrowed from nuclear physics, where Erast state was the lowest energy state with a given angular momentum of a nucleus. Here, again, momentum translates into angular momentum because we are on the circle. So actually, these are Erast states in the very close analogy to the 5 minutes? Over? Over. My goodness. So I have to show you one more thing. I think there was still some kind of the puzzle. What are really these second branch excitations? And just want to show you that actually one can understand them very easily on the ideal gas case. Because if you have ideal gas, then the lowest excitation of a given total momentum is, of course, realized by sending all the excited atoms to the lowest, the first excited state, right? Because then you have energy which grows linearly with K. On the other hand, if you, instead of shifting a lot of these atoms to the first state, you take one atom and put it into the K state, that of course forms a parabola, and of course parabola immediately, you can understand, goes very quickly to a model of a Bogoliubov excitation in this ideal gas case. What we studied quite a lot recently and wrote a paper about is this study of this lowest branch of the ideal gas, and we've shown that actually these ideal gas fellows are having dark solitons if you again refer to the single measurements or single measurements of a single copies of a system, very much as Saha said, except that in this case, of course, everything is analytic. There is no numerics at all involved. My last part, which I completely skip, is about rotons. And rotons we found fiddly, of course, with the combination of contact, attractive, and dipole-dipole repulsive interaction, and actually showing that under proper conditions, these two lines can cross, and Bogoliubov type minimum state, which as you know is Roton, can appear as the ERAS state. And that's actually the last result I wanted to show you, and I will not show you because of lack of time. Thank you very much.
Thank you.